All right, this is where we left off with that fundamental theorem of calculus. Officially, this is part 1. We will have part 2, don't worry. It's just one half of it, right? So this is the important connection between a definite integral and an indefinite integral. The definite integral can be evaluated by using the antiderivative. So if I want the area under a curve, I could do that by using geometry. Great. The limit definition of the integral. Great. Now I also can use the antiderivative as a shortcut. So take the antiderivative, evaluate at the top bound, minus the antiderivative evaluated at the lower bound. And if you need to look back at your drawings for that, we had some good illustrations. Something to note, f needs to be continuous. That's because if you're collecting area underneath a curve, we can't have any big jumps or discontinuities, because what does that area look like? We're not really sure, right? If you think about that from a graphical perspective. Something else to think about is when you are looking at a graph, you can see the antiderivative as the area under a curve. So we see the derivative as the slope. We see the antiderivative as the area under a curve. Okay, so antiderivative practice, find a function whose derivative is this. So what this really means is for each one of these, we are finding the indefinite integral with respect to our variable of integration x. So go ahead and pause, take a minute, fill those out. Hopefully those went okay for you. It asks, do the problems above have unique answers? And the answer is no, right? These are families of functions. I don't know if this is the cosine graph just as the parent function, or maybe this cosine graph has been shifted up, right, to this midline of 12, right, plus c. Or maybe it was the cosine graph, but it was shifted down to a midline of -10. I don't know. But I do know that the derivative of cosine results in negative sign, and that's the family of functions that we've created. All right, so indefinite versus definite integrals. As I mentioned in the last one, an indefinite integral refers to a family of functions, antiderivative. A definite integral is a number. It's the area under a curve. Remember, it's the signed area, so we get positives depending on which way you're traveling, or negatives depending on which way you're traveling and collecting that area. Now, our connection between these two is as a shortcut to find the definite integral, we can use the antiderivative, which we'll talk about with this example. So we have the same function, 3x squared. This one is the indefinite integral. This one is the definite integral. So the indefinite integral just means take the antiderivative. So the 3 is just going to hang out. This becomes x to the third over 3 plus c, which really then is just x to the third plus c. This is our antiderivative. This one then says to find the definite area between 1 and 4 underneath the curve 3x squared. Well, prior to today's lesson, we would have had to use the limit definition of the integral and have this whole mess of a limit summation. Now I can use my shortcut. What this says is to take the antiderivative, which I just found was x to the third, and then this is some new notation for us. We're going to evaluate from 1 until 4. So instead of writing plus c, the family of functions, we are evaluating this antiderivative from 1 to 4. So what that means is I need to find the big purple area. 4 cubed minus the small red area. 1 cubed. Well, 4 cubed is 64. 1 cubed is 1, which gives us a total area of 63. This area underneath the curve is exactly equal to 63 without having to do that limit summation. Okay, so again, we take the antiderivative, we evaluate low bound, high bound. Take the big area minus the little area. All right, so an example like your homework. Graph and find the area of the region and evaluate the definite integral. So the first thing, if we are going to graph this, right, we can use our calculator to help us. We can use a little bit of AAA knowledge. We can find our roots at 1 and 5. We know this parabola opens upside down. I am looking to find this lovely area. All right, well, to do that, I could use the whole limit definition of the integral, this whole mess, or I can use my newfound shortcuts. And the new shortcut would say take the antiderivative. All right, well, I'm going to do that first. So this is going to be negative x to the third over 3 plus 3x squared minus 5x. There's my antiderivative, and I'm going to evaluate it from 1 until 5. Okay, so antiderivative evaluated from 1 to 5 would say plug in the big bound first, right? I'm finding the big area, negative, the opposite of 5 cubed over 3 plus 3 times 5 squared minus 5 times 5. So that's the big area minus my smaller area is negative 1 cubed over 3 plus 3 times 1 squared minus 5 times 1. And if you go through and do all that by hand, that's all well and good. You can also use your calculator and that math fraction. Survey says that this blue area is equal to 10 2/3 or 32/3 with that math fraction. All right, so now we can actually use our calculator to check all of our definite integrals. So I mentioned the other day we have this thing Math 9, which is function integrate. So if I go to Math 9, I'm looking to integrate from 1 until 5 of my function. Okay, well this is where we're going to get some fancy calculator things going on. If you go to y equals and you type in the function negative x squared plus 6x minus 5, and we look at that graph, maybe, there we go. There's our function, okay? Now, when I go back to my home screen, instead of having to retype that whole function, I can say I know that it is stored as my y1. So I can get there a couple ways. I can press alpha and then F4, and look, there's y1. I can just choose that, and I'm integrating with respect to x. Okay, so that's one way to get there. Oh great, I got 10/3. Another way to get there is to do Math 9. We are going from 1 till 5, and I can go to variables, y variables, function, y1. Okay, there it is. With respect to x, I get 10 2/3. Another way I can check this, if I go to my graph, from here I can choose second calculate. There's the integral sign, so I'm going to choose number 7. This is my function y1. My lower limit is 1, enter. My upper limit is 5, enter. And there's my area underneath the curve. Okay, so just a lot of different ways to check your answer, and we will get used to using that y1 feature as our functions become more complicated. Because instead of taking the risk of retyping negative x squared plus 6x minus 5 every time, you can just store it once in your calculator and then use it for the duration of whatever problems you're working on. Okay, so last time. A fundamental theorem of calculus. The area under a curve, the signed area, okay, so it takes into account positives and negatives, can be found using geometry, using the limit definition of the integral, or with our newfound awesome shortcut. First take the antiderivative, then evaluate at b, big area, minus evaluating at a, little area. Okay, so this note about signs, a definite integral might involve regions that fall under the x-axis. In this case, it's a net result. So it's like your displacement, not your total distance traveled, of positive and negative areas. And the way we've seen this before was with the sine curve on your quiz a few weeks ago. If this area is 2, we would call this area negative 2. So the integral from 0 to pi of sine of x is equal to 2. The integral from pi to 2 pi is equal to negative 2, which means that the integral, I'm actually going to call this positive 2, but below the x-axis, we'll go with that, from 0 to 2 pi of sine of x dx is equal to 0, because these things will negate each other. If this sign was representing our velocity curve, I would have traveled 2 miles to the right of my house and then 2 miles to the left of my house, which puts me right back at my house. If this was some other curve, let's say like this, and this was 5 and this was 2, I would have traveled 5 miles to the right of my house and then 2 miles back, which has given me a displacement of 3 miles from my house. And again, we'll work with all of this more. Hopefully this was a good introduction for you. Fundamental theorem of calculus, a new shortcut for finding the area under a curve, evaluating a definite integral.